Hello? Ah. I think this is working. Okay, alright. Hello everyone. I'm not gonna really do an introduction, but basically we're gonna be reading AI papers. Yeah. Give me a second here. Let me figure out some of the logistics. It's a bit hard. Let's see if any of these things are even working, right? Let me see. Oops. There we go. Get to the correct paper here. Alright. Well, I'm probably going to be reading this paper about residual vector quantization first. Now this is, I guess, about trying to compress some vectors. My current work is in quantization, but I haven't really dealt with residual vector quantization, mostly doing linear quantization. And I am interested in seeing this different approach that I just discovered today about it. And so this is like a downstream paper applying it to LLMs, right? But I really want to see the original concept here of residual vector quantization, how it works. So Lee et al. 2022. Okay, what is this? This is pretty recent too. Autoregressive image generation using, okay, well, that's not the one I want. Improves data reconstruction quality without increasing sequence length. Okay, extends vector quantized variational autoencoders, 2017 paper. Okay, usually these things get introduced in the 90s, so I'm not really sure why I'm seeing papers that are this recent. Okay, but I'll highlight that to go back to as well. However, despite the advantages of RVQ in data compression, generative modeling, okay. Interesting. Yeah. Generative modeling should also work. Okay. Boy, there's some other logistics I have to deal with. Great stuff. Give me a second here. Okay. And this setup is like kind of hard. What's happening? Okay. Very weird. Interesting. Okay, well, wow, lots of different things to deal with here, huh? First time streaming is really having a bit of a fun time. Damn. Okay. Well, let's see. My video resolution is too high? How does that work? What? Bruh. This is really pretty fun. Let's see. Program output, settings, output, stream output. Okay. Can I change the quality of the output? What's going on here? I cannot change it here. Well, it looks like things are working. So I guess I'm not gonna worry about it right now. Well, it looks like things are working. Huh. Well, okay. Let's get back to it then. Alright. Here we go. Okay, good. Top 10 times. I have to set this up. Crazy. Hopefully smoother next time. Interesting. Well, okay. Let's get going then. All right. 2017 paper by iteratively applying vector quantization to the residual of the previous quantizations. Okay. Sure. Process results in token. Okay. Just trying to find the original paper here. Okay, well, basically you sample more, and whenever you quantize a particular vector, you'll get a loss, right? Like basically like what parts of the vector you actually destroyed by quantizing, right? And then you try to quantize that vector that you've destroyed by projecting it to the same, I'm assuming the same codebook of vectors that could actually be represented as quantized values. Sure, that's fine. Okay, the oldest paper I can see is this one. Neural Discrete Representation Learning. What? Is that really? Vector Quantized Variational Encoder. Okay, that must be it then. Sure, let's search this up here. And you guys can't see it, but I'm just pulling it into my repository real quick. Oh, great. I can't actually do it here. Okay, got it. Neural Discrete Representation Learning. Okay. DeepMind. Okay, this is nice. Seems like we should probably learn something from this. Vector Quantized Variational Autoencoder. Okay, it differs from VAEs in two significant ways. Encoder network outputs discrete rather than continuous codes. Okay. Prior is learned rather than static. Yeah, this is fairly technical. That's good. Does it have any GitHub? No. Okay, if we could, I mean, clearly this quantizer is learned like an actual neural network. So what if we use a neural network to quantize models and decode them rather than some sort of code book? That'd be kind of interesting. Okay, well, I guess the neural network would be a code book in some sense. But it would be like a learned code book. Conserves the important features of a data. Okay, right. So you've got these kind of generative modeling. Okay, they say generative modeling works well. And then people train these models on the pixel domain. Okay. This is a latent space idea. So as the best generative model will be those with latents, without latents, but a powerful decoder. However, we argue for learning discrete and useful latent variables. Sure, okay. So you got discrete instead of continuous latents. And by the way, this is, I think, now been proven to be true. Like, Yan LeCun and everyone else says that you should be looking at models that don't train on latent space, instead join embedding models that have the loss on the embedding space instead. So you have to read those papers fully, but I think we'll get something interesting out of them once I do read them. Learning representations is continuous features, having the focus of previous work. Okay, right, so they discretize the representations. Okay, language is discrete. Sure, that's true. Speech is represented by a sequence of symbol. Okay, but like speech modulation and sound and music are not discrete, generally speaking, I think. Images can often be described concisely by language. Furthermore, discrete representations are a natural fit for complex reasoning. Okay, well, syllogisms, I guess, are discrete. But I'm not sure if complex planning is symbolic. Is complex planning inherently symbolic? Maybe not. So, variational autoencoders, their encoding eventually lands you into a space. Basically, like, you basically get out a parameters for a distribution, and that distribution is then sampled from using your decoder. So really you're learning the encoder, which is a neural network, and a decoder, which is a neural network, and in the middle there's like some sampling procedure with some parameters. Parameters, I guess, would determine basically what kind of output samples you get. Like if that variational autoencoder has is modeling things as like a 1D Gaussian, then you have a mean and you have a standard deviation or like variance, and then you could input both of these values and then you would be able to sample, right? Or you could like have a image that isn't generated, and then you have that image basically like be passed to the encoder, and then that gives you a point, right? That gives you a point which like it will be encoded as into a point, and then that point can be sampled out and give you and eventually give you a output. So variational autoencoder. I believe I have a paper on this, right? Yeah. Sample Z from, okay, this is it. Training time variation autoencoder is a feed-forward neural network where the probability of a given x given a particular z, which is to say like the value of the hidden variable here, right? And then so the loss here is like twofold, right? So first is like you're doing a KL divergence, right over here. You're basically trying to make sure that the normal distribution is like fairly similar to whatever distribution that you're giving it into. So the distribution here that is dependent on whatever your x is, which is your input, as well as the variance given whatever x is, right? So basically like what your encoder gives you, you want to try to map that to a normal, right? Okay, and then after that you sample from a normal, like, so this is like undifferentiable behavior, right? But this is treated as basically as an input, a fixed input, and then you multiply these guys, right? Like basically the mean here, right? And then the variance, okay? And then you multiply these guys, and then you get out a transform distribution, right? The transformer distribution is now this, right? This is the mean of the x, and then the variance of x, right? So you get out, and then you want to try to make that as close to the normal distribution as possible after encoding. So then you have a decoder. Decoder goes through and basically just decodes that back into something in the space of x, right? Whereas this is like actually like now z, or in this case I guess they write it as epsilon. Well, yeah, after this, so this is like noise, right? But then that gets added to whatever z is. So z is sampled from the normal distribution that is transformed by whatever these parameters are, and then that's sampled, right? So that is a particular value in the embedding space, and then that gets passed to decoder. So just to go over here and make sure what we're doing is correct here, right? We use sampling to estimate this, but getting a good estimate will require passing many samples. Yeah, it's not super clear how this is parameterized and what gets passed in there. We should search C, I guess. Figure 5. Yeah, so let's look at this, right? DQZ dependent on X. Yeah, what is this? Does the total number of bits is the sum of the two-step minus a penalty we pay for Q being suboptimal encoding. That should, like, this suboptimal encoding should be Q of X, right? Z should be Q of X. But there's like an extra term here that I didn't see before. Q of X, P of X. Oh, probability of Z. Okay. So P is basically like the ground truth. And then why are they using D? Is that KL divergence? Oh, yeah. Oh, they have different notation? What? Why do they have different notation? See, they use KL here and then they use D in the actual paper. Okay, this is weird. Alright. Sure. Now that we have a brief review of variational autoencoder, we can go ahead and briefly look at the discrete variational autoencoder now. So, simple to train does not suffer from large variance and avoids the posterior collapse issue. Okay, interesting. Posterior collapse, I have not heard that like particularly as much. Posterior collapse. Collapse. No, not even a mention. Interesting. It's a very fun thing to do here. I mean, I feel like we ought to not do that. Right, anyway. Right. So we can equip our decoder with the speaker identity. Right, okay, this is just saying how good it is, right? I don't actually know what it is yet. Perform just as well as continuous. Okay, that's really interesting. So you discretize everything and you still perform just as well as the normal VQ-VAE. I mean, as the normal VAE model. Interesting. Okay, well, discrete variables. Oh, what is the original paper for variational autoencoders? Autoencoding variational Bayes. What about this? Stochastic propagation, approximate inference. Okay, I guess I should visit 23 here because that's the original paper. 23 original. At least it seems like this is pretty much the original paper. 2013 paper, and this is 2014. Okay, so this is like variational autoencoders are actually pretty recent then. Many alternatives for training VAEs. Okay. Multi-sample objective. Okay, I guess there's multiple ways of training it even. Huh. Concrete gumball softmax distribution. Interesting. This is interesting. Yeah, it seems a bit different from most of the language model papers I've been reading, or quantization papers. There's much more math or theory, it seems like. It's continuous latent variables, where one can use Gaussian reparameterization, which is the one we read about just now, the Gaussian reparameterization trick. Sure. Image datasets do have a much larger dimension size. Okay. Pixel CNNs are convolutional autoregressive models, which have also been used as a distribution in the decoder of VAEs. Okay. So they use it as the encoder, I suppose. Finally, our approach also relates to working image compression with neural networks. Okay. Scalar quantization to compress activations. Okay. Oh, interesting. Yeah, work that's in parallel to yours. Huh. Annealed over time. Interesting. Hardy-soft relaxation approach. Well, okay. Perhaps the work most related to our approach are VAEs. Encoder, which parameterizes a posterior distribution QZ given X of discrete latent random variables Z. Right, so what do you mean discrete latent variables? It's continuous latent random variables Z given input data X. A prior distribution, well, that's definitely not discrete. Like, I'm pretty sure they meant to do continuous. And a decoder with a distribution Px dependent on Z over input data. Interesting. Decoder is distribution X dependent on Z over input data. Yeah. Yeah, okay, yeah. So one of them, encoder trying to get Z, and then decoder is trying to get X from Z, where X is your input data space. It's in your input data space, so images, right, in the case of what they mentioned above. Typically, the posteriors and priors in VAEs are assumed. The posterior distribution is based on X. The prior distribution is just based on Z, and it's assumed to be normal, I'm pretty sure. The posteriors and priors are assumed normally distributed with diagonal covariance, right? So this is like, there's no weird, like, the Gaussian, like, is like basically just symmetric in all aspects. Right? There's not like, oh, you have like high value on the first dimension, and that means high value on the second dimension. There's no relation like that. It's all independent. All right, so discrete latent variables, okay, which allows for reparameterization trick to be used. Extensions include autoregressive prior and posterior models. What is that? Normalizing flow. Okay. Normalizing flows is important. That's like diffusion models and such. So it's what they said for this. I see. Variational inference was normalizing flows. And what is this? Density estimation was real NVP. Huh. Inverse autoregressive posteriors. I have not heard of those. Interesting. We introduced the VQ-VAE. Okay. Sure. Finally, we're going to get to the method here. Alright, how do they work? Latent embedding space, where k is the size of the discrete latent space, the k-way categorical. Okay, this is just a fancy way of saying there's like k choices, I suppose. What about this d over here? And d is the dimensional. I see. Okay, so like there's a d. There's k possible vectors that could be represented. Each vector is a continuous vector that's of the same dimensionality as whatever you're trying to quantize. So in this case, d is chosen by the user. I'm pretty sure. EI is okay. Every EI is inside of d, right? And there's k of them. Okay, the model takes an input x, is passed through an encoder producing output ZE of x. So this is an encoding that is probably of the same dimension as d here, which is part of the R, I suppose. The discrete latent variables are calculated by nearest neighbor lookup using the shared embedding space E. Okay, are then calculated. Oh, right, okay, so I guess this is not quantized yet. This is just a continuous vector. Yeah, okay, and it looks up basically the nearest vector in E that's possible, right? To that the nearest vector in R to Z sub E of x. The input to the decoder is the corresponding embedding vector that's given in equation 2. Equation 2, right? Okay. One can see this forward computation pipeline as a regular autoencoder with a particular nonlinearity that maps the latents to one of k embedding vectors. Okay, sure, that's fine. The complete set of, I guess the nonlinearities can be anything. Okay, but it's not differentiable, which is probably a problem. How do they deal with that? Like this search for the nearest vector is definitely not differentiable. Okay, the embedding space E, the encoder and decoder, right? For the sake of simplicity, they refer to the embedding space also as E. Oh, right, I guess that's kind of, well, wouldn't it be, oh, right, that's just the real k times, okay, yeah, sure. So E is actually the space itself. Right, okay. For sake of simplicity, we use a single random variable Z to represent the discrete latent variables in this section. Okay. However, for speech videos, we actually extract 1D, 2D, and 3D latent features respectively. Oh, okay. So they're like sometimes vectors. Really? They're only 1D, 2D, or 3D? I thought they'd be bigger. That's interesting. Okay. I thought it would be like you know, latent features are like 10 or like 13. Okay, I guess for VAEs you actually use something like 1, you know, like 1 or 2 parameters for the parameter space. Okay, well, let's see. Posterior categorical distribution QZ dependent on X probability is defined as 1 hot as follows. Okay, right, yeah, so 1 whenever the K is the argmin of whatever. Yeah, so whenever K is the nearest. Right, okay, but this is intuitive. Right, so where ZE of X is the output of the encoder network. Yeah, okay, let me actually explain, because I might end up writing something like this in the future, so it might be good to be more familiar with it, right? So we've got X, which is our input, ZE, which is a particular vector, particular vector after projection by the encoder, and then EJ is some particular vector that is part of E, the embedding space, right? And you're trying to find the L2 norm of the difference, which is just how close it is. Okay, interesting that they're not using cosine, they're using just L2 norm difference. So this is just like the this would be the length of the vector between the member of the embedding space as well as the output of your encoder, right? So then that it basically asks like, what is the nearest member of the embedding space to the output of your encoder, and then if the particular the particular member of your encoding space that we're currently considering, right, is the same as the smallest, right, then it's 1, right? So the probability that Z is equal to K, well, okay, it's not the probability, right? Basically you will assign the latent variable Z to K if K is in fact the vector in the embedding space that is the closest to the output of your encoder, right? And then 0 otherwise. Okay. We view this model as a variational autoencoder in which we can bound log P of X with elbow. Oh boy, okay, gotta remember how that worked again. Or maybe not, let's see. We can bound the probability of P of X inside in the decoder. Our proposed distribution QZ equals K given X is deterministic. And by defining a simple uniform prior over Z, we obtain KL divergence constant equal to log of K. Okay, I mean, how would you assume that the distribution of like the prior for Z is uniform unless like this is not always the distribution over Z depends on what E is, like what the embedding space is. And what the data set that you're trying to quantize is. The representation C sub E of X is passed through the discretization bottleneck by mapping onto the nearest element of the embedding as given in equations 1 and 2. ZQ of X is equal to EK. Fine, you know, this is just the quantize, you want to quantize X, right? And then K is the same thing. This is the closest member of E, right? And then this is just saying, okay, this is a function. This is another function. This function will give you E of K. This function will give you a distribution. This function will give you a single value over here. Right. So note that there's no real gradient defined for equation 2. Yeah, we can approximate the gradient similar to the straight through. Okay, I see this around a lot, the straight through estimator. I never actually looked into it hard enough, I think. Wait, this might be a good one because Bengio paper. Joshua Bengio, let's go. And just copy the gradient. Wait, is that his first author paper? Hey yo, it's pretty good. All right, well, I'm definitely gonna read that one then. Just copy gradients from the decoder input to the encoder. Okay, wow, that's incredible. Just copy the gradients from the decoder input to the encoder output. So you're just skipping it. I mean, like, literally, you're just skipping the fact. Like, you are ignoring the fact that this encoder exists. Like, that this function has at all any impact on the gradients to the encoder. All right. I guess maybe this works because you're assuming some sort of like uniform distribution, but I'm not clear on what the math for that is. So that's kind of interesting. What mathematical properties is allowing us to use a straight through estimator in this case? Well, have it work well. During forward computation. Okay, and what is this other thing they mentioned? Subgradients through quantization operation. I've never heard of this before. Never heard of this operation before. Is it possible? Like, is it useful? Like, it seems useful. During the backward pass, the gradient is passed unaltered to the encoder. Okay. Sure. And during the backward pass, the gradient is passed, okay, since the output representation of the encoder. Okay. The gradient retains useful information about for how to. Wait, what happened to my mouse? What happened to my mouse? Okay. No. Since the output, okay, sure, there's a same d-dimensional space. What do you mean by useful information for how the encoder has to change its output to lower the reconstruction loss? Oh, I see. Oh, I see. Okay. Right. Okay. So basically, this works because you expect the quantization operation to not significantly affect the value of the input to the decoder, right? So if this whole like quantization and dequantization thing didn't actually change your vector by much, which should be the case if your quantization is good, then like that output is like basically can be treated as the input, right? So that output and the input could be seen as like basically the same exact thing. And if it's the same exact thing, then obviously you can back propagate through it, right? It's just obviously the quantization is not like 100% correct all the time, so it's not actually like that. But it's close enough, right? Because it should be unbiased. Like, it should not be like heavily biasing like it so that maybe like one particular dimension of the vector is like more heavily weighted than others. The gradient can push the encoder's output to be discretized differently in the next 4 passes. Yeah, okay. In figure 1, specifies the overall loss function. Oh, I accidentally highlighted a bunch of stuff. Oops. Okay, maybe let's look at the figure first then. A figure describing the variational autoencoder. Visualization of the embedding space. Okay, so you've got a CNN, which is, I guess, your encoder. And then that gives you some representations, E sub E of X, which they're drawing like some sort of a 3D matrix. Don't know what that's about. I don't know why it's so long either. Like, what is it trying to say here? Like, this is like a bunch of 2D. I mean, okay. Odd. Oh, for images, it's like a 3D vector. Okay, that's not a 3D vector though. That's like a, I don't know what this is. Embedding space is some predefined embedding space, okay? You are generating some Z. What the hell? Why is it drawn this way? What is it trying to do here? E53? What is this? Why is there a bunch of them? Huh. Odd. I don't like this diagram. Is not very good in my opinion. Like, are you trying to project every single one of these vectors? Like, what's going on here? Q, Z dependent on X. Right, that is Z, but Z should really not be like, what is this grid? Like, are we assuming there's like some 4x4 grid of vectors I'm trying to like encode here? Like, that looks like one image. That should give you one vector as a result of an encoding. I don't know what this whole block thing is. What about, what's this? Z, Q, or X? As in QZ depending on X. See, this one makes sense, right? This one makes sense. So this is your the vector you get out of applying Z sub E to it, right? So this is Z sub E of X, right? So you applied ZQ to X. Now you get Z sub E of X. Oh, okay, no. Yeah, you apply the encoder, right? So Z sub E of X is the encoded value here, right? And then the little purple dots are the possible values, right? Members of E, the embedding space, right? And then you got this being the closest thing to it, right? E sub 2, right? And then after you go to the quantization function, right, you get zq sub q of x, and that z sub q of x is what gets passed into the decoder, right? And that would be basically a member of the embedding space, right? So that member of the embedding space, after you like quantize it, right, you use that member of the the index of that member of the embedding space to get the vector represented by that member of the embedding space. There we go. And then that gets passed to the decoder, so it's a vector that gets passed to the decoder, and then you get a generating output, and then that output has a loss on it, right? That loss is probably something like a difference, like a pixel-wise difference, right, between the images, right? Right. That loss generates something you can backpropagate, right? You backpropagate the loss, right? And then, boom, that loss gets passed straight back over to zq of x, right? So that loss is actually on zq of x, not on ze of x. I don't know what the arrow here is saying. Because the loss is calculated, loss is calculated based on zq of x, because that's the only thing the decoder had access to. But it will be used by ze of x, right? It will change the weights in ze of x, right? And then that will push the next forward pass to generate a to have a slightly different ze of x, right? Which will result in a slightly different ze of x, right? And then that means the next time around, perhaps the quantization function will quantize it to a different embedding point, right? And then you get a different loss and all that again. Okay. All right, now that's clear. Equation 3 specifies the overall loss function. 3 components that are used to train different parts of VQ-VAE. So the first is the reconstruction loss, okay, which optimizes decoder encoder. So the estimated, okay, so that's what we just explained. Due to the straight-through gradient estimation, the embeddings the embeddings obviously receive no gradient, right, because we've skipped it. Therefore, in order to learn, so it learns the embedding space as well. We use one simplest dictionary learning algorithms, vector quantization. Oh, that's where it comes from. Vector quantization is used to learn the embedding space. The vector quantization objective uses L2 error to move the embedding vectors towards the encoder outputs. Interesting. Okay, I don't like how this is not end-to-end. Like this, not end-to-end usually just means it's worse, right? But let's not speak too much before I understand how this works, right? So towards the encoder outputs, okay, as shown in the second term of equation 3. Where's equation 3? Okay, down below. Because this last term is only used for updating dictionary, one can adaptively also update dictionary terms as a function of moving averages of e to the z sub e of x. Okay. Right, let's not worry about that for now. Finally, since the volume of the embedding space is dimensionless, it can grow arbitrarily if the embeddings e sub I do not train as fast as the encoder parameters. What do you mean the embedding space is like you can have an arbitrary k, I guess. To make sure the encoder commits to an embedding and its output does not grow, we add a commitment loss, the third term in equation 3. Okay, thus the total training objective becomes the log of px dependent on z sub q of x, right? So this is the outputting the original image given the quantized image, which is like impossible. You'll never do that unless your quantization like actually like throws away zero information, right? But like that's what autoencoders try and do, grab the most essential information. Okay, which really, now that we look at it, like the joint embedding architecture definitely will be better than this, because sometimes like the output cannot be reconstructed if you throw away a bunch of information, and the loss function really matters in this case. Like, loss function, if it's dependent on the pixel space, will essentially mean that you're trying to make sure as little pixels change as possible, but sometimes it's not important. Like, for example, if you're trying to predict that there's like a cup on the table, right? But you don't actually know like what pattern is on the cup. Like maybe the cup has a bunch of like cool texture and stuff, but it's actually impossible to predict what exact texture it is. And you don't really care about that. You really care about the fact that the cup is on the table and not phasing through the table or something like that. Well, phasing through the table might actually be like less different pixel wise than like having fancy patterns on the cup that you get wrong. So, loss definitely does matter here. Yeah. Anyway, perhaps not the greatest example. The one that Yann-LeCun always gives is like trying to predict like from one picture of an auditorium, right? What would happen? What would be the image you see if you were to pan the camera to another part of the auditorium? Like, there's going to be chairs there. How are you going to predict like what the people who sit there look like? It's impossible, right? There's like, unless you see some like really weird like reflection trick, like still it's going to be like very hard to understand who is like what kind of people are sitting in the auditorium, right? But you can certainly predict that there's going to be more chairs, right? Except obviously like the kind of loss that's used here, like a pixel-wise loss, right? That's not gonna be prioritizing the fact that there's chairs rather than people. So it's gonna try to like force the model to predict exactly what people are sitting there and like where and like what they're wearing, and that's impossible. So this is a waste of resources. Right. Okay, what is this? SG. What is this SG function here? Like, what is that? Stop gradient operator. Constraining its operand to be a non-updated constant. Okay. Operand, I'm assuming this guy. Yeah, so you're not trying to propagate this part of the loss to Z sub E, the encoder. You're simply... okay, this is really funny actually. This specifies you're not updating Z sub E using this loss, which is trying to like minimize the difference between members of the embedding space with the product of Z sub E, right? And this is all well and good, right? Except when you consider that over here, you're skipping this whole operation of like the quantizer, right? And you're not mathematically writing it anywhere here, even though like you're like doing a thing on the gradient. You're saying skip the gradient here. And then same thing here, you're saying skip the gradient on this guy, except only in this case do you actually specify it. Interesting, mathematical notation kind of things. And then same thing here, there's a stop gradient on E. Okay, I don't know about this case though. What is this? Why is this term? This is actually changing Z sub E, I'm pretty sure. So how is this? Why is that a thing? Let's see. The encoder commits to an embedding and the output does not grow. Oh. So this is to regularize the encoder. So you are training the encoder. The embedding space is dimensional. So what does that mean? Vector embedding space is dimensional. There's definitely a dimension to it that's specified. Oh. Dimensionless as in like the actual values inside of the vectors could grow to infinity. And this ensures that it doesn't do that and keeps close to whatever the initialized values of E are. Which is interesting because you have to initialize that somewhere. I'm pretty sure this is like an arbitrary point currently. Wonder if there's a initialization that actually matters for this. Zero partial derivatives of technically constraining its operand to be a non-updated constant. Interesting. With respect to the encoder parameters. Okay, see, decoder optimizes first loss term only. Encoder optimizes first and last losses. Yep, okay. Embeddings are optimized by the middle loss term. Yep. We found that the resulting algorithm to be quite robust to B. Okay, that's good. To beta, I mean. And does not vary for values of B, beta ranging from 0.1 to 2.0. Okay. In general, this would depend on the scale reconstruction loss. Okay, well, okay, if it's robust, I'm just not going to worry too much about it, I think. Okay, yeah, I mean, really depends on the scale of E, I think, right? Scale of E as well as the scale of, like, scale of the difference between the encoder and the, what's it called, the embedding, members of the embedding. In our experience, we define n discrete latents. That's why we saw that square. You use n discrete latents, a field of 32 times 32 latents for ImageNet. Okay, the resulting loss L is identical, except we get an average over n terms for k-means and commitment loss, 1 for each latent. And then the log likelihood is evaluated based on, what is this, like a sum over P of zk, which is what exactly, the kth latent, and the probability of x. So this is like the decoded image given the encoding, the probability of well, okay, this is like so abstract. This is like a mathematical representation of something. Like, this is what mathematically it will be ideally, except this is never the case because probability distribution of z of k is only ever estimated because you only have a finite amount of training samples. Yeah. Okay, gonna take a quick break here. Bit tired. Okay, we're back. We're back. All right, let's see here. Okay. Log likelihood of the complete model can be evaluated as follows. So how are we doing this? The decoder is trained with z equals zq of x from map inference. Okay, yeah, that was the absurd mathematical formulation they have. Okay. Yeah, okay, right, from map inference. I'm assuming this is the pass-through thing. The decoder should not allocate any probability mass to p of x given z, because z is not zq once it has fully converged. Oh, for z, I see. Right. So if the model is if the decoder is converged, it means that it understands the only possible values it could ever receive are within the embedding space E, which is some like trained embeddings, right? Like, so a finite number of possible vectors, and then we can simply write. Is this actually true though? Like, I feel like because it's a neural network, it will not be perfect at doing this, right? Like, so it will assign some probability mass to things that are not within the embedding space E. We'll see. I haven't actually trained one of these things to know that. Maybe we should test this. So, does it actually assign probability mass this way? Okay, we empirically evaluate this approximation in section 4. Thus we write log p of x is defined as approximately log p of x dependent on log p of x dependent on zq of x. What is that? The probability of x given the probability of an input image given the quantized latent variable produced by the encoder and the quantizer. Yeah. Right. Multiplied by the probability of okay, so this is the prior probability of the latent variable. No, this is not the prior probability. This is just the probability of that latent variable. This is the probability that given x, like that we have encoded x into some member of the embedding space. So it's the probability given x of a particular embedding member of the embedding multiplied by the probability that we actually correctly decode back to x, right, which is again our input or image given this embedding, right? Yeah. Sure. Why? So what do they specify this for? We empirically evaluate this approximation. We can also write the p log p of x is greater than this. Sure, that seems reasonable. But I don't know why greater, not like lesser than. So it's at least this. The probability of. Oh right, because this is, you assume that this may not capture the entire probability of x, right? Because if the probability of x depending on that embedding, so the probability of x given z sub q of x is actually assuming that is the probability that you have in fact correctly decoded z sub q of x into x, but there's a chance that you don't actually do this, right? So this value here, the first part of this will only ever be less than 1, right? And that's why you can say greater than. Great. So the prior distribution over the discrete latents is a categorical distribution and can be made autoregressive by depending on other z in the feature map. Actually, I'm thinking about this again. Like z of k is depending on q, probability log p. Is this the probability of the entire model? Okay. Yeah, this is pretty much the probability of the entire model. Z of k is, I'm assuming it's just z sub q of x. Yeah, the kth vector. They used k 2 times. They used k both to specify the number of members in the embedding space, as well as how many of these vectors they produce from a given image. So they decode using a block as well. They use a 32 times 32 block to decode it into that image again, which is interesting because how do they do that? Questionable, I suppose. Like, how do they decode? Like, you see 32x 32 latents. Like, they have to up project that back into some large 252 or something like this latent. I don't know, like, how is this even ingested, for example? Do you just encode them separately? Do you encode all these vectors separately? Like, what's going on here? Like, interesting. Right, the prior distribution over the discrete latents P of z is a categorical distribution, right? Because the embedding space is discrete and can be made regressive by depending on other z in the feature map. While training on the vector quantized variational autoencoder, the prior is kept constant and uniform. Okay, after training we okay, the prior is kept. How are you keeping the prior constant and uniform? That's interesting. Oh boy, terms. Ancestral sampling. Oh, my selection is off. What's going on? Oops. Ancestral sampling. How? Use pixel CNN over discrete latents for images. Wave night for, okay, so they have different decoders, I guess, right? Oh, is it prior? No, so pixel CNN might be the encoder, actually. Training the prior and the VQ-VAE jointly, which could what is this? They are taking a pre-trained encoder. Pixel CNN. Wait, let me make sure of this. What is Pixel CNN? Pixel CNN. No, it's definitely encoder because that's not a generative model. When did Pixel CNN get introduced? Pixel CNN. What? The two variants were proposed in the original paper, Pixel CNN and two-dimensional LSTM. Where? Did what? Pixel CNN. Where? What are they referring to here? Like, what? Is this just such a common, like, baseline or model that they don't even feel the need to cite it? Okay, Pixel CNN are convolutional autoregressive models which also having use the distribution in the decoder. What? Okay, so they actually might be decoders, looks like. Interesting. So what are they meaning here? Auto-regressive distribution, so we can generate. So pixel CNN is a decoder. Huh. As a decoder. Interesting. Why is this not trained jointly? Oh, is it because you're only training decoder and you only see, wait, no, you're definitely seeing the decoder as the entire thing. That's interesting. I don't know what's going on here. Where does this come into play? Okay, let's move on for now. Oh no, it's we're into experiment results. So this is the compression ratio. Wow, 4 or 5 bits per dimension is pretty good. Each of these dimensions used to be like 16 bits. Or 32 even. Okay, let's see how does this work? How do they actually run it? We train these models using the same VAE architecture as CFR10, where varying the latent capacity, the number of variables, as well as dimensionality of discrete space. The encoder consists of 2 strided convolutional layers. So standard, like CNN type thing. The decoder is also standard, like basically like a UNet kind of thing. Yeah, so it's basically like a UNet kind of thing. And there's a bottleneck in the middle. Right? So we use the atom optimizer. That's pretty standard. We use 50 samples in the multi. So this is like a pretty small amount of data. Interesting. So pretty comparable, it seems like. Good compression. Images have redundant information. By compressing them to a discrete space of 32x32x1. Right. It's a K. Embedding size of 512. It's pretty big. So you are in fact decreasing this size by, what is this, like a couple of 4 times here, and then another 3 times by reducing the channel size. Like 12 times, pretty good. Reduction of 42.6 in bits. What? What do you mean times 8? What is this times 9 thing over here? What? I see. They're counting the fact that it takes 8 bits to store each of these values. takes 9 bits to store each of the 32x32 values, because the k is equal to 512, right? Whereas the number of possible colors also is only 256, right? Which is 8 bits, but you're using 512, which is 9 bits, right? This is like an okay comparison, I suppose. 9 bits is like not really used though, because a byte is 8 bits, so maybe the k equals 512 is not the most fair thing ever. Model images by learning a powerful prior. Okay, over Z. Okay, so reconstructions. Wow, this is like a decent reconstruction, I suppose. You can definitely still tell like what's going on in images. But it's also definitely blurry. Like if, I don't know, like if it's like, see, like if this was more conscious of what's important in an image, it would have made sure the people over here are not blurry, right? And it could like blur out other things, except it's trying very hard to capture this insignificant dent in the dirt here, as well as like the sky, like the patterns in the sky, which is really not necessary. But as a consequence of the loss, right? Loss is still pixel level difference of some sort, I'm pretty sure, at least. Yeah. So reconstruction, even. Yeah. Okay. Okay, the original Pixel RCN paper, finally. Okay. Yeah, it is a decoder. Let me grab that paper real quick. What do you mean? Samples drawn from Pixel RCN mapped to pixel space was decoder. Can be seen if you wish. Samples from a VAE with a Pixel CNN prior trained on ImageNet images. What does that mean? What do you mean a Pixel CNN prior? Like, what? Okay, isn't the output of a pixel CNN the actual image? How is this getting where can we have a diagram where we see where the pixel CNN is? Like, where is it here? Because that feels like the last stage decoder here. Like, it's taking in the latents. Well, I mean the quantized, yeah, the discrete latents here, and it's giving us that image. So it is the decoder? What do you mean it's mapped to pixel space with a decoder? I'm guessing I don't know. Interesting. Isn't the last stage of the decoder? We're training second VQ-VAE on a pixel CNN decoder. Oh, okay. Huh. A prior sampled on the latent space. A deconvolutional model decoder. Is that figure 4? Oh, figure 4. Good. What do you mean a pixel CNN? Like, what does this even mean? We're trying second. Okay, from the first VQ-VAE, you're stacking these variational autoencoder now. Okay, that's reasonable. I've seen that done before. Huh. Posterior collapse. If the latents are ignored because the decoder models X perfectly. But, okay, but how is it able to know what X to model? What? Three x9 bits. Interesting. This environment can be compressed just to 3x9 bits. That's incredible. Okay, well, not compressed perfectly, that's for sure, but compressed much better than I thought it would be. At least the colors look like semi-consistent. And there's only what, like 3x9 possible. Oh, okay, well, not a 3 times no, yeah, 2 to the 3x9, right? So 2 to the 27 different combinations. Actually, that is a lot, isn't it? What is that? 2 to the 27 is 134 million different possible images. Okay, that's like not a lot, but not as lot. Like, yeah, that's not as large of a number as I thought it would be. Great. CNN. What are we doing here? What is this? Is this still okay? There's some audio reconstructions as well. Okay. WaveNet architecture. Well, I'm just getting stuck on this. I mean, usually I don't take this long reading papers, but this one's a pretty important paper, I suppose. It's got a bit more math. The decoder's condition both latents and a one-hot embedding. Okay. What is this? Encoder has some static convolutions. Okay. How's decoding work on this? Phenomenological. Okay. Interesting. Interesting. Looks like there's some support for the fact that these latents actually mean something. Damn, there's even a video kind of VQ-VAE. Interesting. Okay, I'm getting really tired. It's been 1.5 hours. Okay, it makes sense. I think after reading the conclusion and trying to clarify that one issue, I'll be ending it. Okay, I'm like basically checked out. But okay, I can't even read the conclusion. I want to try to figure out what this pixel CNN thing is going on though. Like, how is that? What's the first mention of this pixel CNN thing? A powerful decoder. Okay, but like how? Measured by log likelihood. Measured by log. Oh. Basically, if you have a okay, so if you have a decoder, you give it random inputs, it might already generate like likely instances of the data set. And you basically have to just measure like what is the probability of generating members of the data set. And that probability is high for some decoders just inherently. How do they test for that? Huh. Pixels in over discrete latents. Okay, this is probably. Oh man, I really want to find this out. What ancestral sampling is this? What is ancestral sampling? The easiest way of understanding ancestral sampling is through a simple Bayesian network with 2 nodes. 2 nodes have associated but newly the stage true and false. X is the random variable indicating if the sky is cloudy, Y is indicating the presence of rain. We can safely assume X causes Y, meaning that there's direct edge from X to Y. Okay, X has the probability distribution true equals 25, false equals 75. Node Y rain has a prior distribution that depends on the value of X. Okay. If X is true, then Y is true. So this is a conditional probability. Y given X is true, has this probability distribution. We have to estimate joint probability of X is equal to true, Y is equal to false. I mean, the probability the sky is cloudy and it is not raining. Okay. Well, wouldn't you just have the probability of X multiplied probability of Y given X? This is just like a chain rule, like a product rule kind of thing. You start with some parent node. You draw a sample from its distribution. We pick X equals false. Okay. Sample from the table of Y, taking account that X is false, or 20% chance that Y is true, 80% chance it's false. Okay. We have to repeat this process n times and count how often you get the target combination X true. Holy sh! Okay, the proportion of successful attempts and more the total number of attempts gives you a probability of. Okay, so this is an empirical estimation kind of trick. And you have to sequentially pick all the variables. Wow. As the size of n increases, you're guaranteed to converge. Okay, but this is like if you have a large, if X had like 512 choices, which it does, in the context of the paper we're just reading, then that's like a whole lot of choices, that like a whole lot of samples you have to do. Okay. Forward sampling. Forward sampling really makes a lot more sense than ancestral sampling. Let's make a quick note here, right? So follow the actually let's read what the context of this is before we write an explainer here. Whilst training a VQ-VAE, the prior is kept constant and uniform. Okay, the prior as in the prior of Z, the latent variables. Ah, right, I believe they do mention this. So prior Z latent variables is uniform, so equal probability for each member of the embedding space. All right. And then we have an autoregressive distribution over Z, P, Z. What is PZ? Probability of Z. Could generate X by ancestral sampling. Huh? What do you mean, like an autoregressive distribution? What is an autoregressive distribution? over the discrete latents for images and a wavenet for, okay, I guess like the input to pixel CNN must be some some value, and it's like probably pre-trained. So what kind of value are we talking about here? Like, what are you feeding into this? Are you feeding the latents directly? How can that be? Like, the latents directly is some arbitrary size that you define in this paper. Like, there's no way pixel CNN takes in the same like latent size unless you specifically designed it that way, which I guess we only find out if we read this paper. Alright, well, first we'll find out what a autoregressive distribution is. Okay. Yeah, sure. Current dependent on previous. Yeah, but what is previous? Okay, how can a distribution be autoregressive unless there's multiple distributions? Not autoregressive models. Okay. No. Autoregressive distribution. Okay. Oh, there it is. Autoregressive. Ah, it's a pixel CNN thing. Looks like I gotta read what pixel CNN is. So that's what's going on. Posterior collapse, like, the latent's ignored. Like, yeah, that's interesting. Like, how does the latent get ignored, right? I mean, you're only generating output based on the input, like based on the latents, which tells you what output to generate. How much probability gives the input? That may or may not depend on the input itself. Oh, interesting. Remember, you're not outputting with the decoder a point but a distribution. Interesting. The decoder is giving you a distribution over images. Right. And you're just measuring the probability of you generating your input. If you pick any autoregressive network, take samples from it to make a data set, then you train VAE with a latent, where the decoder finishes as an autoregressive network. Where the decoder finishes an autoregressive network of at least the same capacity as the generator, then that most likely will ignore the Z and just learn the same function. I mean, like, if you train VAE with latent. Oh. What do you mean, take samples from it? I don't know. If you generated the data set yourself, okay, but like, how are you? Okay, if you generate the data set yourself, I suppose you might just recover the same network as the original model that you used to generate the data set. But how are you even measuring like the difference between the output? Like, how are you even training the new model? Like, how are you maximizing the probability of an input being generated by your new model? Like, you output an image, right? Like a CNN, like your decoder outputs an actual image. not a distribution. So what's going on here? If we can model the output, the true distribution can be expressed as a function from the same class. It will learn to ignore the latent. If your data is if your data is not Gaussian, the assumption is wrong. You will never be able to learn Px dependent on Z, ignoring Z. However, this is up to your assumption. Notice how much information you can gain from Z depends on how flexible the decoder is. Yeah, but what if you're not depending on anything? How can you get the probability of X at all if you can model the output? The true distribution can be expressed as a function from the same class. What? It will learn to ignore the latent if it can. There's no other input. There's the latent is the only input to the decoder. Okay, maybe I'm just not following their argument here. Imagine X is coming from a diagonal Gaussian and you have. If the decoder is efficiently possible, then the training objective okay, I want to search this again also because I saw another one that was VQ-VAE specific. Oh, look at that. That's the exact sentence that I was confused on. When K is equal to, doesn't mean the encoder. For image generation, the encoder grid of the latent codes, each spot in the grid, a code from the code book is selected. So if you have 8 times 8 grid latent codes, I think you have, yeah. Now to sample this space to generate a new image, you can randomly pick a code from the code book at all 64 spots. Generate something, but it won't follow correct distribution of images it was trained on. Right. Okay. Yeah, you can't sample, right? You can't just randomly sample, right? So a pixel or RCN or transformer is used as a sequence generator to generate a plausible code sequence. Oh. You can see there was a random selection from the code book and then have it predict the next. Oh, it's all because you have that weird block grid thing that we saw. Okay, so the latent codes are not just one latent code. It's like a bunch of latent codes that are related to each other. You can see there was some random selection. Okay, then predict the next one condition the first two and so on to have all 64 codes picked. It works exactly like LLMs like ChatGPT when you use transformer to create the image. And quantization performed by VQ-VAE makes this possible. It selects indices from codebook one by one as a sequence until it has enough to create a full image. Wait. So that's what they're talking about was the prior. So the prior is the RCNN, and if your pixel CNN is like too powerful, then you can end up. No, I still don't see how you can end up just skipping the latent codes. Like, it's not possible. Like, what? Can be made. Wow, the prior distribution is a categorical distribution, can be made autoregressive by depending on other Z in a feature map. While training VQ-VAE prior is kept constant and uniform, which is not autoregressive. After training, we fit an autoregressive distribution, so that when we can generate, so you're fitting it. So you're training a pixel CNN, so you can generate X via ancestral sampling, which, okay. So then when you generate ancestral sampling, what you're doing is you're looking at the first, oh wow, this is like a huge space. Your ancestral sampling means basically, oh, but that's basically what the transformers, the autoregressive model is going to be doing anyway. It's like it's picking something for the first code, and it's picking something for the second code, and so on and so on. And that's your sampling process. Dude, what the fuck? Just say you use a like an autoregressive model. Just say you're picking a seed latent P of Z and using an autoregressive model to generate the rest of the code blocks, and then you pass that into the decoder and you get a freaking like output image. Like what? Just say that. What? Okay. All right. What is this all like, an ancestral sampling, autoregressive distribution? Come on. Come on, bro. All right. I guess it made me learn these words, so that's kind of nice. Oh, okay, yeah. Right, let's note this, I guess. Only during training, during inference, you are providing one seed code, right? So one vector, and then an autoregressive model like a transformer or pixel CNN will generate like the rest of the vectors, right, in Z sub Q of X, which is a grid of vectors that then is passed to a decoder you trained to generate an image. Incredible. So that's what it is, folks. That's what it is. And probably we should read Pixel CNN, right? Like, just real quick, let's just take a quick look at this. Singular and negated Pixel CNN architecture. It's a RN, it's a LSTM kind of thing. Well, it's like RN kind of thing. It's not a CNN, bro. No wonder it is a okay, it is an autoregressive model, and like, I mean, I guess the CNN probably somewhere here. But yeah, why is it called a CNN? It's not convolutional. I mean, it is an autoregressive. I mean, it is like recurrent, I guess. Gated pixel CNN. Okay, yeah, it's an autoregressive one. All right. Thanks for listening, guys. And Rishi, I guess. No one else is here. All right. Bye.